Hi everyone, let's move on to our last section in this chapter, which is on pulleys. Okay, so in the previous section, we had talked about tensions in the rope or the string, pulling cars and trailers. Now, however, a rope or string connecting two objects doesn't need to be straight. For example, you could be using a rope passing over a pulley to lift a crate. As before, if the string is inaccessible, then the magnitude of acceleration of both objects will be the same. If the pulley has some mass, or if there is friction between the pulley and the axis, it rotates around, then the magnitude of the tension will not be the same at both ends of the string. However, if you make some further modeling assumptions, then the tension is the same throughout the string. So let's have a look at an example for pulley. So here we have a pulley hanging from the ceiling, and the man is pulling the string over the pulley. And on the other end of the pulley, there is a box with some weight. So the man is pulling the string or the rope with a tension, and then the tension will pull the box upwards with an acceleration. Because we would assume that the string or the rope is inaccessible, that means the acceleration throughout the string will be the same. And also we would assume that the string or the rope is light, so that means we can ignore the mass. Okay, so here are the summaries for the two modeling assumptions. Again, it's very important for you to remember them and what it means and how it's used, as they could be very easily asked at the end of an exam question. We can explain that. So if we assume that the string or the if we assume that the pulley has a smooth surface, that means there is no friction between the pulley and its axis, which means the tension in the string is the same on both sides of the pulley. And again, we should assume the pulley is light, so we can ignore the mass. And that will mean the tension again will be the same on both sides of the pulley. Now, the presence of a smooth light pulley doesn't alter the method used for connecting particles in the previous section. Note, so there must be some friction between the pulley and the string, otherwise the string would be slippery over the pulley. But in those questions we're going to look at, we don't need to consider the friction force yet. Okay, so let's move on to look at one example. So in this question, it says a crate of mass 52 kilograms is attached to a light rope hanging over the edge of a wall and passing over a smooth pulley. A man pulls the other end of the rope, keeping it horizontal. The crate is moving upwards with acceleration of 0.3 meter per second squared by the tension in the rope. So here I have already shown the diagram. Now, just bear in mind that normally the diagram won't be given to you, and you have to draw the diagram yourself and add all the forces acting throughout the string by yourself. So I would strongly suggest you to practice that when you're doing exercise. Okay, so here in this diagram, so there will be a man standing over here pulling the rope, and on the other end of the rope attached with a crate of mass 52 kilograms, so the weight is 52 g. And because there is tension going through, so the crate is being pulled upwards with acceleration of 0.3 meter per second squared. So we're looking for the tension in the rope. Okay, so really what we need to do is to consider just the force acting on the crate. So for the crate, we have F equals to ma. So what is the resultant force? Well, if the crate is pulling upwards, so that's our positive direction. And you can see only two forces acting on the crate would be the tension and the weight. Tension is going upwards, which is the same direction as acceleration, so that's positive, T. The weight is acting downwards, so be negative, so be minus 52g. And that equals to the mass of the crate, which is 52 kilograms, times by the acceleration, which is 0.3. So you can then put a calculator and then work out tension T equals to 52 times by 0.3 plus 52 G, and then remember G is 1.8. So T equals to 525 Newton. And that's it. We don't really need to consider about the man on the other end. Okay, so hopefully that's an easy example to start with. Let's look at another one. Okay, so now a string could also be passed over a fixed peg instead of a pulley if the peg is smooth so that the string slides freely over it. The tension on either side of the peg will have the same magnitude. So let's have a look at this example. A box of mass 12 kilograms rests on a rough horizontal table. So here's a box and here's a table. It is attached to one end of a light, inextensible string that passes over a smooth peg. So, but just remember, it works the same, whether it's for the peg or for the pulley. The other end of the string is attached to a small object of mass 4.8 kilograms, as shown in the diagram. Given that the system is in equilibrium, which means all the forces balance out, we're going to find the magnitude of the frictional force between the box and the table. So again, here is the diagram with all the forces labeled already. But remember, if you want to do it as a practice, you can pause the video and don't look at this diagram and try to label all the forces by yourself first and compare with the diagram I have shown you here. Okay, so let's talk about this diagram with all the forces labeled. So over here, for the object hanging here, we have the weight acting downwards, which is 4.8 G. And of course, there will be a tension pulling the object upwards. Now, there will be a tension pulling over here through the string over the peg. And horizontally here, there will be a tension pulling over the peg here as well. And there is a box of mass 12 kilograms resting on a horizontal table, so the weight is 12 G. And if it's resting on the table, we now know that there must be a normal reaction force R acting perpendicular to the table. In this case, it would be pointing upwards. And there is a frictional force to stop the box moving towards the right-hand side. So that means the frictional force will act in the opposite direction, so towards the left side. And there is a tension pulling the box, and that will be towards the right-hand side. So because this is a light inextensible string, so that means the tension throughout the string will remain the same. Hence, we use T for all of them. Okay, so we're going to find out the frictional force. Now, firstly, well, we don't know what the tension is horizontally. Okay, so we should work out what tension is, and we could start by looking at the forces acting on the ball first. Now, because the system is in equilibrium, so that means the ball here, the forces should balance out. So for the ball, the T, tension acting on the ball should equal to the weight, which is 4.8 G. So straight away we know that the tension should equal to 47.04 Newton. So that's good news because now we know that T is 47.04, so the T and T and T and T should all equal the same. So the tension acting on the box will also be 47.04 Newton. So let's consider the box. Now we're looking for the frictional force, which is the force acting in the horizontal direction. So we just need to consider all the four horizontal forces acting on the box. So in this case, there's only two, the frictional force and the tension. And again, because the box is in equilibrium, so the two forces should balance each other out. So straight away, I now know that the frictional force F should equal to the tension. So that means that would also be 47.04 Newton. Okay, the only difference between the frictional force and the tension would be that they are in the opposite direction, and that's it. But because we're only looking for the magnitude, so here is our answer. Great, let's look at the next example. Okay, so you should always remember that the tension in a rope or string exists only as long as it is taut. Once a string goes slack, the tension force becomes zero. So let's look at our final example. Okay, so in this question, it says a particle P and Q are connected by a light inexcentric string passing a smooth pulley. So again, I have now shown you the diagram, but if you want, you should try to draw the diagram yourself before you're looking at my diagram, as most of the cases and most questions in exam, you will not be given the diagram with all the forces labeled on it. So that will be a good practice for you to do right now. Okay, so let's have a look at this diagram. So we have particle P and particle Q. Now we've been given the mass of P is 2.3 kilograms, so the weight is 2.3 G. And the mass of Q is 3.1 kilograms, so the weight is 3.1 G. Initially, Q is held at rest and at 80 centimeters above the floor, and P is 0.9 meters below the pulley. The particles are released from rest, and the system moves freely under gravity. Find the speed of Q when it reaches ground. Okay, so now let's just think. So we already know that P has a weight of 2.3 G and Q has a weight of 3.1 G. So just by common sense, we know that Q is heavier. So when we release the object from rest, Q will start to pull P up, and the Q will start to drop down towards the ground. So now we can see the arrows for the acceleration. Q is moving downwards, so the acceleration for Q is pointing downwards. P will be put upwards, so the acceleration will be going upwards. Now be careful, because it's connected by the same piece of rope or string, so the acceleration will remain the same for both particle P and Q, just in the opposite direction. And also there will be tension throughout the string. So for Q, there's a tension pulling upwards, which we use T to label it. And for P, there will be a tension upwards as well, and it will also be T. Okay, so now part A, as we said, we're going to find the speed of Q. Right. So now let's try to use F equals ma for both of the object P and Q. So let's consider what is happening for P. Okay, so for P, now remember going up is the positive direction. And we have F equals ma. So the resultant force would be, well, T, which is going up, and a negative weight, so be taken away, 2.3 G, and that will equals to M, which is 2.3 times by A. Okay, now that's our first equation. Let's consider Q. So for Q, it's still A for the acceleration, but now we're taking downwards as our positive direction. So in this case, when we use our F equals to ma, the weight is 3.1 G going in the same direction as acceleration, so that's positive. But tension is going upwards, which is against the motion, so that'll be negative. So 3.1 G minus T will equal to M, which is 3.1, then A. So can you see in both of the equations, we have two unknowns, which are the tension T and the acceleration. And we know that the tension is the same, so we can try to make T the subject and substitute into another equation. So we will get from this equation, T will equal to 2.3A plus 2.3G. And that's substituted into the second equation here. So we'll have 3.1G minus the entire equation for T, so we minus 2.3A minus 2.3G, and that will equal to 3.1A. So now we know that, well, we can move this 2.3A to the right hand side, so we have 3.1G, take away 2.3G, so that would give you 0.8G. So that equals to 3.1A plus 2.3A, so that would be 5.4A. So point a calculator, replace G with 9.8, you will get your acceleration A equals to 1.45 meter per second squared. Okay, so now, because we're looking for the speed, so we don't really need to work out the tension yet, okay? So now we have to use SUVAT, S-U-V-A-T. Right. Okay, so we are trying to work out the speed of Q when it reaches the ground. So in the question, it said Q is being held at rest at 80 centimeters above the floor. So in this case, if we consider what's happening to Q, the displacement or the distance Q traveled will be 80 centimeters, or that will be 0.8 meter. Okay, Q was held at rest, so the initial velocity is 0. We don't know about the final velocity. We just work out the acceleration is 1.45. Oops, sorry, I think I've just done. Let's cross this one out because actually we're actually looking for the speed, which is the final velocity of the Q. So that's our question mark actually, and we don't know the time. So let's cross the time out. So let's think about a silver equation which does not involve T. So hopefully you have found the formula we need. And that would be V squared equals to U squared plus 2AS. So we have v squared equals to u, which is 0 squared, plus 2 times by a, which is 1.45, times by s, which is 0.8. And you can put that into calculator, and don't forget to square root to get the v. So we'll get v squared firstly equals 2.32. So v equals to square root of 2.32, and that would be 1.52 meters per second. And that's your answer for part A, which is speed of Q when you reach the ground. Okay, so there's part B for this question as well. So let's have a look now. Now, for part B, I think we need this sentence as well. So here it says, when Q reaches the ground, P continues to move upwards. Okay. Right. If so, when Q reaches ground, so you can see I have now changed the diagram. Q is now dropped onto the ground, but what we said before in the question is P will continue to move upwards, and we're going to find the time it takes P to reach the pulley from the moment it is first released. So in the question, we know that the particle P before is 0.9 meter above the pulley, so that would be the distance it traveled. Okay, so right now, let's be careful with this question here. Okay. Now, so in the previous part, in part A, do you remember what is happening? So when Q reaches ground, how far it traveled? It has traveled 80 centimeters already, which means at that time, P will have been pulled up by 80 centimeters already. So now, let me draw a diagram, just quickly show you what is happening. So imagine P was here before, and that's the pulley, the top. So previously, before everything's moving, the total distance between particle P and the pulley is 0.9 meter. And when Q dropped onto the ground, for that time, P has already moved up by 80 centimeters, so 0.8 meter. So that means after Q reached the ground, P will continue to travel for another, not 0.9 meter, but actually another 0.1 meter. So just be very careful with the distance traveled here, okay? So you can't use 0.9 straight away. You have to draw a little diagram to figure out the actual distance P traveled. Okay, so from the previous part, we have now worked out that by the time Q reached the ground, or in other words, by the time when P traveled up to 0.8 meter, the speed was 1.52. So let's write down our super. S, U, V, A, and T. So from this moment, if you look at the green part, you're writing here, okay? For this part of the journey, P will continue to travel for another 0.1 meter to reach to the pulley. What is its initial velocity? So by the time it traveled for 0.8 meter, at this point, it would have the same velocity as Q, which means that would be 1.52. So that will be the answer you actually worked out from part A. Now, we don't know its final velocity when you reach the pulley, so we can cross that out. What is the acceleration? So some of you might use the acceleration we used in part A, and that won't be right. And that is because for this part of the journey, Q is no longer pulling P anymore, and P was moving upwards freely. So the acceleration acting on P in this case will actually be due to gravity. So A will be the 9.8 and it's going downwards. Okay, so I have kind of already assumed that we're going up as the positive direction. So that means our acceleration, which is due to gravity, will equals to negative 9.8. Okay, so be very careful here with your acceleration, because this could be a common mistake in exam. Right. Now, I think we can then work out the time. So let's think. Well, which formula do we need? Does it involve V? So that would be S equals to UT plus a half AT squared. Okay, so S is 0.1, U is 1.52, T is unknown, plus a half comes by negative 9.8 comes by T squared. So this will become a quadratic equation, and you can put in your calculator, and you should get two answers. One of them would be T equals to 0.0947 or 0.216. Right. So now, which answer are we going to use? Well, if you think, what would happen? Okay, so imagine P is here and I start to go reach to the pulley, and this first time it will reach to the pulley will be this answer. So that would be the smaller answer. Okay. So what would happen? Why we would have a different answer here? If you link back to what we did previously, talking about the particle moves upwards and then down, so like a projectile, we always get two answers at a time, because if I draw a diagram out like that, so this would be the smaller answer at the time, so that will be the first time when something reached to a certain height, and it will continue and it will go down, and this will be the second time when something will reach a similar height. Okay, so in this case, we'll actually ignore the large answer, because we are not looking for this position here. We're looking for the first time when particle P reach up to 0.1 meter. Okay, so this is the time P continues to move after Q hits the ground. Well, what about before Q reaches the ground? We actually haven't worked out the time of that. Okay, so we need to do another super equation and work out the time take Q to actually drop down to the ground. Right, see if we can squeeze in the gap here. Right. So what is happening for Q? Q reaches ground. Okay, so let's do another SUVAT for Q this time. So the distance for Q traveled was 0.8. U was 0. V we work out in part A, that was 1.52. And A we worked out also in part A, and that was 1.45. And we're looking for T. So actually, we know all the other for information, so we just have to pick a simple formula to use. And I would say probably this one would be the easiest, which would be V equals to U plus AT. So V is 1.52, U is 0, A is 1.45, and then T. So T equals to 1.05. So now we have the two things. This is the time taken for Q to reach the ground, which means this will be the time taken for P to travel up by 0.8 meter. So that's 1.05 seconds. And this is the time for P to continue moving upwards after Q reached the ground. So that's when P moved up by 0.1 meter, and that would take 0.0947 seconds. So that means altogether, the total time taken for P to travel 0.9 meter to reach to the pulley, that would equals to 1.05 plus 0.0947. And that will come out to be 1.14 seconds. And that's your final answer. Okay, so this example is a bit more harder because you have to be really careful with what is happening to each individual particle and how they travel. Okay, so now let's do some exercise. So here's exercise 22E. When you do all the questions, please make sure you draw a diagram and label all the forces acting on each object. And also you should label the tension throughout the string as well. So this is question 1, question 2, question 3, 4 and 5. And you can see here for question 4 and 5, there's no diagram drawing for you. So you should try to do a diagram. If you're not quite sure, just try to have a look at the other diagrams we've been looking at an example, or back to questions 3 and 2, how the diagram will draw for the pulley or for peg. Question 6, question 7, 8, 9, 10, 11, 12, and at the end, question 13. And here are the answers.